Hello guys, and welcome back to the reaction zone. In today's lesson, we're going to look at how to derive the Nernst equation. Now, the Nernst equation shows the relationship that exists between electrode potential and concentration of ions in solution. Specifically, the Nernst equation shows the dependency of electrode potentials on concentration of ions in solution. Now we're going to look at how to derive the Nernst equation and other similar equations that are also necessary. Now, for an electrochemical cell, the change in Gibbs free energy, which is represented by delta G, is equal to minus NFE. Now let that be equation 1. Also, for a chemical reaction in equilibrium, the change in Gibbs free energy can also be expressed as delta G is equal to delta G naught plus RT ln K as equation 2. The difference between delta G naught and delta G is that delta G is the change in Gibbs free energy, whereas delta G naught is the standard change in Gibbs free energy, that is, the change in Gibbs free energy at standard conditions. Now, I can equate equations 1 and 2, and when I do, I will have equation 3, which is minus NFE is equal to minus NFE naught plus RT ln K. Now, looking at the left and right hand sides of equation 3, NF is common. So I can decide to divide both sides of equation 3 by NF. And if I do that, I will have minus E is equal to minus E naught plus RT ln K over NF. And then, if I decide to divide across by minus 1, I will have E is equal to E naught minus RT ln K over NF as equation 4. Now, this equation 4 is actually Nernst equation. But then, there are several versions of the Nernst equation. We're going to look at that now. Now, in equation 4, we have natural logarithms, ln. Now, if I want to express Nernst equation using logarithm to base 10 and not natural logarithms, equation 4 is going to become E cell is equal to E naught cell minus 2.303 RT over NF log K base 10. Now, when you look at equation 5, which is Nernst equation expressed using logarithm to base 10, I can actually replace some of the parameters with their actual values. For instance, I can replace R with 8.314 joule per mole per Kelvin. I can replace the value of F with 96,500, that's Faraday's constant. And I can replace T with the value of room temperature. Room temperature is 25 degrees Celsius, which is also 298 Kelvin. So if I impute the values of R, F, and K in equation 5, I would have E cell is equal to E naught cell minus 0.0591 over N log K base 10. So the meaning of some of these parameters in the equation needs to be looked at. R stands for molar gas constant, T stands for temperature, E naught stands for the EMF of the cell, E stands for electrode potential of the cell, F stands for Faraday's constant, and N stands for number of electrons involved. So it simply means that equation 4 is Nernst equation using natural logarithms. Equation 5 is an expression of Nernst equation using logarithm to base 10, and equation 6 is simply a simplification of equation 5. So please take note of these differences. Now, at equilibrium at 25 degrees Celsius, Gibbs free energy, which is equal to minus NFE, is equal to 0. Now, if G, which is equal to minus NFE, is equal to 0, it therefore means that the value of E will also be 0. So, it means that in place of equation 6, which is Nernst equation, can replace E cell with 0. And when that is done, the equation becomes 0 is equal to E naught cell minus 0.0591 over n log k base 10. So everything that is here can be taken to the left-hand side of this equation, since the value of E cell is 0. And when that happens, the equation becomes E naught cell is equal to 0.0591 over n log k base 10. Now this formula can be used to find the EMF of the cell. Now, I can also decide to find the potential of a single electrode. Now let's not forget that in a galvanic cell, there are two half cells. There is the anode half cell where oxidation occurs, and there is the cathode half cell where reduction occurs. So if I want to find the electrode potential of the anode half cell, for example, which is where oxidation occurs, it means I'll be looking for the oxidation potential of the anode. And that is simply going to be E oxidation, which stands for oxidation potential of the anode, will be equal to E oxidation naught, which is standard oxidation potential, minus 0.0591 over n log the concentration of ions at the anode base 10. So this formula here is used to find the oxidation potential of the anode. Now, if I want to find the electrode potential of the cathode, bearing in mind that at the cathode in a galvanic cell reduction occurs, it means I'll be looking for the reduction potential of the cathode, and that is going to be E reduction. E reduction stands for reduction potential of the cathode, and it will be equal to E reduction naught, which is standard reduction potential, plus 0.0591 over n logarithm to base 10 of the concentration of ion at the cathode. So this formula here can be used to find the reduction potential of the cathode, and this formula here can be used to find the oxidation potential of the anode. So in summary, we have looked at how to derive the Nernst equation. We have looked at the various versions of the Nernst equation based on whether we're making use of natural logarithms or logarithm to base 10. We have also looked at how to have gotten the formula to find the EMF of a cell, and we have also gotten the formula to find the oxidation potential of the anode as well as the reduction potential of the cathode. Now, in subsequent videos, we're going to be looking at questions that will involve us to make use of these formulae to solve questions. Until then, thank you for watching, and see you in the next lesson.